What's this mean? I've just evaluated the derivative, f dash x, okay? So I'm going to plot that on, and I've got two graphs here. I'd like you to sketch these Cartesian planes beneath each other because we're going to do some comparisons with them. It's a very, very simple graph, right? F dash x, okay? But there are some great things that you can notice about it. For instance, when you think about your original x squared parabola, right? Let's think about its gradient, okay? And this is actually something I'm going to encourage you to put onto the diagram itself. Over here on the left-hand side, the gradient, all the way from negative infinity up until 0, except for 0, the gradient along here is negative. These are minus signs, okay? It's a decreasing function for x is less than 0, right? And when you have a look at this, you can see that this negative is matched here by the fact that the derivative is negative for x is less than 0, right? And in fact, the further away you go toward infinity, the more negative it becomes. What does that correspond to geometrically? What does that mean up here?
Negative infinity and positive?
Yeah, it's super negative. That's really, really steep, right? Which is why if you draw this further, it sort of seems like it's going vertical. It doesn't, but it seems like it. More negative down here means steeper up here, okay? Steeper in a negative direction. As you approach on the derivative, as you get closer and closer to 0, the derivative is approaching 0, right? What does a derivative, or should I say a gradient of 0, what does that mean? Yeah, it's not rising at all, right? This is the gradient of the tangent, right? The tangent along here is already on the diagram. It's the x-axis. It's horizontal, right? A gradient of 0 means rather than dropping like a rock, right? I'm slowing down, and then here I stop. I stop. If you want to think about this in terms of movement, it's like I'm dropping down really fast over here, as you'll see in a second. I'm increasing very fast over here, but right there, I stop, which is why this point here is called a stationary point. Not stationary with an E, which is like, ooh, I have really fancy stationery that I got from Typo. I mean stationary with an A, which means it describes a point where there is no movement, right? It is not going up, it's not going down, it's stationary, okay? But not only is it a stationary point, after that point, the gradient is positive. Right? So here are my plus signs indicating that it's an increasing function. You might have seen some of this like diagrams in your textbooks and that kind of thing, right? And what it corresponds to, of course, is that my derivative is positive. Derivative is positive if x is greater than 0, which means it's increasing. And the further you go in this direction, tell me, when is this derivative, when is it going to stop getting bigger? Never. It never stops. It just keeps on going and going and going, which corresponds to geometrically, this is going to get steeper and steeper forever, right? Forever. That's a bit weird. We can't do that in real life, right? Like you can't imagine a mountain that gets steeper and steeper forever. Eventually it stops, right? Or it just levels out and becomes a cliff or whatever, okay? But this literally gets steeper and steeper forever. There's no point you can say, oh, can't go past there anymore. It'll just keep going. Now, because it transitions from going down to going up, this point here, the origin, is not only a stationary point where it stops, this is a word I introduced you before, a phrase, it's also a turning point because the graph is coming down and then it turns around and goes up. Obviously, you can imagine a turning point that's upside down that could go up and then go down if I just slapped a minus sign on the front of this thing, okay? So it is both a stationary point and a turning point, but these two things are kind of like rectangles and squares, right? Rectangles and squares. All squares are rectangles, right? All squares are rectangles, but not all rectangles are squares. So in order to turn, you have to stop, don't you? Right? Like you can't turn around without stopping. But once you stop, you don't have to turn. You don't have to turn. So for instance, here am I walking across the room and then I stop. And I'm not going to turn around, I'm just going to keep going. Right? So there was a stationary point there, but there was no turning point. I didn't go back and face the opposite direction. Okay? Think of a graph. You almost just recently drew one. Did you? No, you didn't.
Yeah.
Oh, you know you did. You did. A graph that stops It's increasing, 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 it stops, and then it just says, no, I'm just going to keep going. I was right the first time, okay? Which graph is the most obvious one? Yeah, the cubic curve, right? The cubic curve, if you just think of the vanilla y equals x cubed, it does this. It goes, stop, stationary point, and then it just keeps going. There's no turn. Stationary point, no turning point. Okay? We'll develop more language to describe this point later on, but that's enough for now. Yeah.
But the derivative is 2x, right?
Yep.
If that's positive, then for example, if I had a point on this side of the parabola, why would the derivative be 2x? Would it be like negative 2x?
Okay, great. So it's like I couldn't have done this. I couldn't have planned this better. I planted you. Okay. So next little bit of notation. Okay. It's not really a new piece, but it's new in this context, right? Remember in function notation, if I say f of say 2, f of 2. Okay. Actually, I take that back. That's a bad example. I'm going to go f of 1. Okay. What that means is you take your function, right? And you say, well, okay, that's 1 squared, that's 1. What is this number? What is that? It corresponds to a coordinate, right? This x equals, this input is my x coordinate, right? And this output is my y coordinate. Agreed? Okay, but in exactly the same way that has this notation, I have this, right? So if I say now f dash 1, right? This doesn't mean how high are you when x equals 1. This means, what is your gradient at x equals 1? And it's 2 times 1, which is 2. Okay? What does that correspond to? Well, at this point, what's the gradient of the tangent that's there? The tangent's going off like that. Okay, my scale's not fantastic, but that's increasing. It'd be 2x, right? I guess it would be a bit steeper, really. Okay, but my scale I haven't really put on there. Okay? Now this means, right, so like I said, you might like to put that on. That's the y coordinate there, f, and f dash will give you the gradient at that particular point, right? So this is the gradient function. This is what happens to the gradient function at that spot, at x equals 1. Now if you consider, well, let's just chuck in some other values, right? Well, let's think about f equals negative 1 on the opposite side, right? Because it's, what kind of symmetry does this function have? It's an even function, so unsurprisingly you're going to get the same y coordinate, so you're at minus 1, 1, okay? But when you pop in f dash, right, when you pop in minus 1 into f dash, you're getting 2 times negative 1, which of course is minus 2. What does that mean? Okay? Yeah, you've got a tangent there, right, which has the exact opposite gradient of this. In fact, by the way, see how this function here is even. This function has symmetry too, doesn't it?
Yes.
Oh, it's
Wonder why that is odd. Why is that? We'll have a look at that a bit later on.